Okay, ladies and gentlemen, it's my pleasure to open the last course of our PhD Open program, last course this year. I'm very happy and honored that we have Łukasz Kaiser with us. And it's some sense a success of our program that we had so many participants to this course that we had to find a bigger room. Maybe we have some guests also from physics department. Łukasz worked in various directions and various branches of computer science. He has a nice page in theory. Well, he graduated from Wrocław, University of Wrocław, and then got a PhD in Aachen, in this famous technical university in Aachen. Well, I had pleasure to serve as a reviewer of his PhD. And at that time, Łukasz worked in, monadic second-order logic and game quantifiers and cardinality quantifiers. But he was also interested in games in more practical aspects. Well, and he had some very bright ideas and then started to work with Google. And he's now in brain team in Mountain View. He will talk about games. So he had contribution in particular to many important projects like Tensor Library and others. And to the end, I would also like to thank Google company for sponsoring this event and in particular providing access to Google servers. Okay, so welcome, Łukasz.
Thank you, Damian. Thank you. Yes, so Damian was a reviewer of my PhD thesis and a supervisor on many papers before. And this is kind of a different topic. So I switched from theory to deep learning. I will make a few connections, but I really want to start with just deep learning. For one, because it's very popular now, and for the other, because a lot of engineering has been invested in deep learning, so it's quite easy to get a basic thing, to get something to train. But I will, later in the lecture, I will try to show you that actually thinking from the theoretical standpoint can help you in deep learning very much. But yes, let's get started just with deep learning. So I want to cover some basics. And what I would like to know is how many of you already know this. So in general, I'm used to a very open style of lectures, so please don't hesitate to ask and interrupt. And I mean, I think it's very important to really understand what's going on in the deep learning code can be 5 lines, but there are a lot of things going on in the background. So I want to make sure that everyone really understands what's happening in these few lines of code. So for today, I would like to do that and maybe train some image classification model. Image classification, like classifying digits or simple images, is like the hello world of deep learning. It's always the first model people train. It's mostly to explain what's going on. And then I want to tell you about sequence models, which is what I've been working on for the last few years mostly. So these are models that generate structured objects, which we encode as sequences. So you can encode as a sequence of bits anything. It can be an image, it can be music, it can be text. And in recent years, these models that generate these sequences or translate from one sequence to another have gotten very powerful. And there are 2 kinds of them. One are deterministic. These are models of functions. You get an input, you have one output. Others are models of relations, probabilistic functions. I will talk about both. And the goal for me for this whole course is that, you understand what's going on, but also that you are able to train one of these models for yourself. And you might want to choose what model and what problem you do. So we will have exercises, and we have some servers and some cloud credits available for those of you who want to train larger models. We will do most of the exercises in something called Colab, which is like a IPython notebook platform where you get a machine. So I hope every one of you will be able to do that. Yeah, so that's the plan. But the point is, it's for you to benefit from it. So if you have something you want to know, something you're particularly interested in, don't hesitate to tell me, and we'll get into it. Because, yeah, I think this slide is on purpose here, because, like, why deep learning? And I think it's a very interesting domain. It's a point I'll be trying to make. But let's be honest here, right? Why? Because it's immensely popular now. And why is it popular? Well, it's popular because it's solved a number of problems that, like, practically people wanted to solve and that have been extremely hard to do. Like speech recognition, getting speech and translating it to text, translating between languages, recognizing what's in an image, recognizing faces. These are all problems that have been very hard. There were separate programs for every one of them. There were, I don't know if any of you remember the old times where people wrote like translators with regular expressions and dictionaries, and like you had to have people who spoke German to write an English-German translator. And now it's all done with machine learning by people who don't speak these languages mostly, and they're much better. And the astounding thing is it's one method doing all of this, right? So it's very inspiring. So, but there is the flip side, right? The flip side is deep learning requires a lot of compute. So you take a bunch of data, you train these models, and this training process is very intensive in terms of computations. So how much computation? Well, so this is the speed of like recent generations of GPUs. Do you guys know what's a K20, K80, and P100? Who knows? Okay. So for those who don't, these are like the previous and one but previous generations of NVIDIA GPUs. They were called Kepler and Pascal. And the K80 and 20 are just like smaller and larger GPU of the same kind. The current GPU is called Volta. It's again faster a few times. So these machines, like a single GPU, gets up to almost 10 teraflops per second. And this is single precision floating point. So it's not exactly comparable with the double precision floating point used in the scientific computing. But to put this in perspective, like there was a list of top 500 supercomputers in the world, right? It came out 3 days ago, and the top supercomputer scores 120 petaflops. And it's 3 times faster than the one a year ago, right? So if you take something called the TPU pod, which Google will be trying to sell you in a few months, you will get 100 petaflops, or maybe 120 if they like optimize it, just for you. So you will get a machine which is as fast as the fastest supercomputer in the world just to train your model. And this machine is like just 10 GPUs, right? Well, not really. In fact, the supercomputer actually has GPUs, and on single precision it has about an exaflop of compute. But this really requires a lot of computing power. And in a sense, it is possible because of this. So like having a server with a GPU is kind of a requirement to do anything more serious here. We will connect to machines that have one of the K20 or K80 GPUs. But for the more ambitious tasks like homeworks, we have the credits and the servers with Pascal cards. Because without it, anything will take 3 days or 3 weeks. With it, you can go down to hours and minutes. And well, since it's became popular, like the number of papers has also followed the exponential curve in recent years, which may be worrying if you like think about how good they are. But maybe it should not be worrying because, so this is accuracy in image recognition. And as I said, so this task of recognizing objects in images, it was like one of the first tasks that was put on computers, and it started before deep learning. So this competition has been going on for years, and it's a set of million images, and you have 1,000 categories. Is it a dog? Which breed of dog? Is it a house? Is it a cat? Every image has like one main object, and you're supposed to tell what it is. And the performance, like human performance, like 75-ish. It's a bit hard to measure, of course, because it depends what human does it. But it was nowhere near reaching human performance before deep learning started to be used. And then there was this first entry by Alex Krzyzewski and Ilya, which, well, got named AlexNet, and it beat all the previous methods, which were very carefully handcrafted for this problem, with this generic network that we will train a very similar one in a few moments. And it already got like 55. And then the beauty of deep learning is you get a good result, and then it starts going up. More data, more compute, more time, better network architectures, and the results just get better and better. So now this image recognition thing is better than human performance at this kind of images. Also, one thing that I want to mention and stress, the deep learning community has a very open culture. So people publish very early. People publish almost everything that gets done. So for a company like Google, 3 years ago, it used to not be obvious that you will be allowed to publish the work you do inside. And I guess the same goes for a lot of major companies. So these are technologies used in products. These are technologies that give companies competitive advantages. So it's absolutely non-obvious that any of this code or papers should be open from a business point of view. But because you kind of cannot hire people in deep learning unless you allow them to publish, this whole field has this extremely open culture. So papers get published, code gets published, and even more, like sometimes code gets published before writing a paper. It's actually in the library that I'm doing, like Noam Shazir, he wrote an optimizer and just wrote a to-do to write a paper. Someone on Twitter found it. The paper ended up including results from people who we didn't even know by name because they were on GitHub. So that's how it works. It's a culture where you just work, put code out, and then at some point you kind of write a paper, but it all evolves very organically in this really open setting. It can be very messy. It's often not easy to understand what's happening, but it's very nice in the sense that you really get access to the things that are happening the moment they're happening. Okay, so in this introduction, I want to give you a preview of deep learning for natural language processing, because this is the field I've worked on most. And this is a preview from 2 years ago, because that was the time where it was still a surprise. Nowadays, if you go to an NLP conference, it's all kind of deep learning. But back then, people were not yet believing in natural language processing that you can use neural networks at all. So I hope you've heard about natural language processing. So this is stuff like part of speech tagging, parsing, named entity recognition, language modeling, which is just generating sentences in a language, translation, compressing things, question answering. So these are the tasks. And the standard NLP pipeline looks something like this. You have a lot of linguists arguing about what is a word and what is not, and then they make a tagger. Or probably a few groups they make a tokenizer. Few groups make different tokenizers, but then people kind of standardize on the Stanford one. And then on top of the tokenizer, people build part of speech tagger. Then on top of the tagger, they build a parser. They write a grammar of English, carefully, argue a bit, then make it a probabilistic grammar, so do some machine learning, and compete on these scores, how to parse a sentence into a tree. And then on top of these parsed things, they try to do something like sentence compression. Cut off some branches of the tree, like some subphrases, so that you get a compressed sentence. And then that might get used in a Google product. Like you ask Google, why is the sky blue? It has like a very long sentence. It tries to compress it and tell you on the phone. So that's how it used to work in like 2014 and 15. And then there was this quite radical idea, mostly pushed by Ilya Sutskever, but kind of course, Schmidt-Huber would say he's been doing this 10 years earlier, that you can forgo this whole stack, that you don't need a tokenizer, tagger, parser, and a compressor. You just gather a lot of data, whereas a long sentence and a compressed sentence, or whatever. One sequence inputs and the other sequence outputs. You gather a lot of data like this, train a neural network, and it will learn to do this. So first of all, nobody in NLP believed you can do this at all. Because it's like, I'll give you a very generic system, one page of equations, and a million sentences translated from English to German, and it will learn translating. And people thought that's just not the case. It cannot work. But they made it work. The first paper made it work with RNNs. And and the results were kind of on par with the previous systems. Sometimes like they were a little worse, sometimes they were a little better. We did the same for parsing, where you like need to have part of speech tags and generate a tree. And people were like, oh, but you're training the network only on sequences. How will they know it's a tree? Well, the network doesn't know, but it almost never makes mistakes in bracketing. So it just learns to bracket correctly. The same was like for language modeling. If you wanted to generate a sentence in English, so people used n-grams. They would like gather databases. N-grams are just tuples of words, right? Which word would probably come after these 4 words? And then you'd apply this to generate a sentence. And the results here are measured in something called perplexity. And even after applying RNNs, people were like, oh, but you cannot go below 40. That's almost impossible. And as it happens with deep learning, the results just get better. I think we're at 23 now. And to give you an idea what this means, because people look at these scores like accuracy, perplexity, and don't have a feeling what these improvements actually mean. So these are sentences generated by a neural network language model, and they're just raw. I mean, the language model, you just sample sentences, so these were not hand-selected. So let's read the last one. Yuri Zirkov was in attendance at the Stamford Bridge at the start of the second half, but neither Drogba nor Baluda was able to push on through the Barcelona defense. So with n-grams, you would see that this is a fluent sentence, right? The words kind of follow grammatically. But you see in the model that it learns which names are names of soccer players. If you train it for long enough, it actually learns which player plays for which team, at least for the famous ones. It learns which teams play at which stadiums. So this model is just trained to generate the next word in the language, but it has a large context, and it starts to really learn like long-term, deeper relationships that just things like n-grams don't even begin to capture. So, and the same happens, I mean, I give you examples from NLP, but the same happens in many domains where deep learning gets applied. You can compress sentences without any parsers. In translation, which we will talk about a bit more, scores are measured by something called BLUE. BLUE is a score that compares the generated translation to the golden translation. And it compares like how many bigrams and trigrams overlap and makes a statistic of this. It's a score that the linguistic community has developed for a while. And again, like, for example, the phrase-based systems, which are before the deep learning, they got to like 21. And I remember in Aachen, which had a very strong machine translation group, like going up by 1 in this score would probably get you a PhD. It required a lot of tweaking, a lot of additions to the large software system. And like the early neural networks were actually not as good. And then the first ones got to this level. But the nice thing is the progress, right? Already, they got to 26 already in 2016. And as you'll see, like nowadays, they're about 30, which is like the human level. Yeah, and they're more fluent, and they start to reflect the style of the question better. The style of the query. At Google, we measured with Google Translate. So because the blue score, it's just a metric of n-grams, it's never sure whether that's what people really care about. So we ask a lot of people, how do you find this translation? Do you think it's better than the other one? We ask people who speak both languages. And the neural networks like scored a really huge improvement on this score as well. So that was from 2016. And some people thought, OK, like at 26 blue, you will not get higher. And then we had a new paper that got to 28 a year ago. And exactly the same model. There were no substantial changes other than making it a bit bigger, training it for longer, and correcting all the bugs. The same model gets to 29.7 nowadays, which is a score. It's the same score that if you take a human translator and he retranslates this, it gets the same on this score. So at least in this metric, it's also reached. So the point with deep learning is it turns out more data, bigger models, and a lot of debugging works better than building hand-tuned systems. And this is one thought that we will be going on through and through. So these are the successes of deep learning. And now how is it all done? So this is somehow an old school view of neural networks, right? So a neural network is supposed to have neurons. So these are like the neurons. And then the neurons on the synapses connecting them to another neuron, they have like weights. And you multiply the signal here by the weight, add them up, apply some function, which is, it used to be sigmoid or tan h, but nowadays it's f of x is usually max x0 in most modern neural networks, which is called ReLU. And then that's the output of this neuron, right? I hope you've seen this before. That's the old style view of neural networks. So you have these neurons, and then they're connected in layers, often in a dense way, meaning everyone is connected to everyone, or in a convolutional way, meaning there are shared connections. Then you have layer and layer by this. So, let's be a little bit more precise. So what is a fully connected, meaning a dense layer of neurons? Is every neuron in this layer is connected to every neuron of this layer with different weights, right? So every of these arrows has a different weight. And the equation is like this, right? Now, in a convolutional network, which was started for images, that's why I'm drawing it like this, but imagine this is a 2D sheet of neurons. So every neuron here, only the 3x3 field is connected to this one. And then you shift the 3x3 field down and to the sides. So this neuron will be connected to a 3x3 field around him on this plane. And the connections in these fields are shared, meaning the same kernel. So these are the weights now, this kernel matrix. The same matrix is applied to the other 3x3 thing. Is this reasonably clear? OK, so there are these two types of layers, dense and fully connected. Dense and convolutions. And now these pictures I've shown you before, I haven't seen them in a while now, because like for a fully connected layer, the way to write it more naturally is just the neurons in one layer, like this thing, think about it as a vector, right? Forget the neurons. It's just a vector of numbers. The weights, when it's fully connected, if this has size n and this has size m, then it's an n by m matrix, right? So the whole thing that a dense layer does is a matrix vector multiply. And then you apply a pointwise function to the result. So throughout, we will have this modern tensor view of things where we operate on vectors and multiply them by matrices. Now, when we operate on images, if we want to have the 2D structure, then we call them tensors. So tensors are multidimensional vectors. And throughout most of this course and also most of deep learning, we will operate on 4-dimensional tensors. And this is a convention, but it's a convention that's so popular that it's just good to learn it. So the dimensions are usually like this. There is a batch because the whole training, as you will see, goes in parallel over a batch of examples. So the first dimension of every tensor is usually just the number of examples that will be processed in parallel. It's not important for the semantics of most models, but it's there in practice. Then there is a height and width for images. And then there is the number of channels, which is, so like for every height and width, there is usually a vector of this size standing above them. Okay? So this is what's usually processed. And then you can have a convolution that, it will look at a, say, 3x3 field on this at every channel and produce a new channel. In case of text, you can think that it's like, say, width is 1 and height is the length of the text. But, well, you could think it's just 3-dimensional. But yes, to keep the same thing. So the tensor view is we're just applying operations, and these operations are mostly matrix multiply, convolutions, and some pointwise functions. 2 tensors of this size, but we apply them with learnable parameters, which are these weights. So at the end of the process, we have some loss. This loss, for example, if we generate one class, then the loss is usually like the minus log of the probability that we generated the true class. We'll talk about this a little bit more. And then what we want to do is we want to update these weights so that the loss will go down, and we update them by gradient descent, meaning we subtract the learning rate, which is some constant, multiplied by the gradient of this loss function, computed with respect to all the trainable parameters, which here would be like the weights and biases, but they could be the convolution kernels, right? So now, how do we compute this gradient? Well, all of these functions are differentiable, and the loss is just a chain of applications of these functions. So to differentiate this function, we just need to apply the chain rule backwards and compute the derivatives. And that's what packages, like modern software packages like TensorFlow, they just do it for you. So you don't even need to worry. The software will go over the construction of this function symbolically, compute how you would compute gradients, and make the gradient update. So what do we need to make deep learning work? Well, we need to make a software that allows us to do these things, right? It needs to be really good at matrix multiplying and convolutions, and it needs to do them really fast because we'll be doing them a lot. it needs to allow you to get the gradients. Well, you have these trainable parameters, so you need to specify and like keep track of them and manage them somehow. Well, and then you want to run it often in parallel in the large scale. So that's the only thing you need to make deep learning work. And, one software package that I want to tell you about that does this is TensorFlow. But before we get to that, are there any questions? Yes?
So what are the channels?
Sorry?
What are the channels?
So for example, if you have a red, green, blue image, then it has 3 channels. It has a value saying how red it is, how blue, and how green. And then in the next layer, you often have more channels. So a convolution is an so let's have an image. Say we make a 2x2 convolution, right? So it will apply to these 4 points. And now every channel of the result will take into account, so it will be a neuron connected to all channels of all these 4 different points. So a convolution of this kind has 2x2 times channels of the input times channels of the output. Has that many parameters. So you very rarely operate on images with just one number inside a neural network. It's usually an image that over every pixel has a whole vector of numbers.
Another question. Can you go back to the previous slide? There is B in those formulas.
Sorry?
What's the capital B?
The B. So normally we don't just multiply x by weights, but we also add numbers to it. So B is a vector of numbers of the same size as Wx. And the reason is, like if you think about it in this view, so you multiply the x's by the weights, and the nonlinearity is often max of, so the nonlinearity f of x is often max 0x, also known as ReLU, rectified linear unit. So the problem is you don't really want a 0 here. You want like a learnable constant. It's a threshold operator that takes the sum and just leave it untouched if it's above some threshold and zeroes it out if it's below, right? So we will maybe talk about it later a little bit, but these are basically threshold circuits. If you thought about computational theory, multiply by weights, add them up, then apply a threshold, except the threshold is of a slightly different form, this max 0x. But it doesn't change the fact that they're threshold circuits. But for them to train well, you want this threshold to be learnable. So you add a bias, a trainable bias vector. More questions? It's important to understand these things. OK. In that case, so I wanted to say, if you want to get into the basics more, then there is a really nice course on Coursera, the machine learning course by Andrew Ng. It goes very slowly, like step by step through linear regressions, explaining all of the basic things and how they connect to matrices and how much it's faster. So if you want to check it out. Yes?
I have a question, because this ReLU function,
Mm-hmm.
it doesn't have a derivative.
Oh, it has a derivative.
Almost everywhere it does.
Yes.
Almost everywhere, and this is enough, right?
Yes.
Okay.
Yes, it's just 1 and then 0. And, you know, for us, almost everywhere is as good as.
Why rel is better than other functions? Sigmoid, or it just works better?
I'm not even sure it always. So, because people tend to think. So here is where. So that's the sigmoid function, right? It's like, you know, e to the x divided by. So mathematicians tend to think that it's like continuous and stuff. For example, it never reaches 1 or 0. So maybe when we get to experiments, you should try to compute sigmoid of 17. And I assure you, in single precision floating points, it's exactly 1. So we are doing this on computers, not on real numbers. Nothing's really continuous. Actually, even the operation of w times x is not continuous because the numbers are cast to single precision. And there was actually a paper showing that a stack of linear layers can do nonlinear computations because of this precision. So the network can actually learn to exploit the fact that the precision is limited. So everything is only approximately continuous here. So, you know, almost everywhere, yes, doesn't affect us. It would affect us more if it was really often, but yeah.
Yes, this is interesting. So what are the limits? So what kind of problems you cannot solve this way?
Yeah, we'll get to that later. We certainly still hope there are none, but but we'll see what are the practical limits and what are the theoretical limits. Yeah, I think that will come a little bit later.
Derivative over logarithm is 1 over x. So what about instability, numerical instabilities?
Yes, they need to be done nicely.
So extra ifs, or do you expect the network to adapt and exploit?
Oh no, the basic operations have very fine-tuned implementations that are numerically stable. Yes, so TensorFlow. TensorFlow is a package, is a software package built with deep learning in mind, but also allowing other operations. It was built with these goals in mind, right? We want to be able to do these basic operations very fast in a distributed way. We want to get gradients, and we want to use it for machine learning. It was the second generation of a deep learning system, actually, at Google Brain. The first generation, called Disbelief, was more like something that's called Torch today. It had like these big objects for every layer. And it proved very hard to maintain going into the future. And then Brain decided to make a full rewrite, change all machine learning software at Google, and do this thing called TensorFlow, which would be way more atomic. So a TensorFlow is a data flow graph. So the things that flow on the arrows are the tensors. The things that are the nodes are operations. And so it's a graph of nodes, a graph usually without cycles, except for recurrent networks, but then you can unfold it. We'll talk about it later. And the things that flow on the edges are tensors. So now you might ask, why do we want to build a separate software system? Because you could do all of that in MATLAB, right? You just have tensors, you multiply them. But as we said, this is something done for large-scale distributed hardware. For example, if you want to build your own hardware that will have no operating system, but just execute these graphs, then you really want a graph. But there are these things called variables, right? These things that we will be learning, which have a state. So it cannot be just a functional graph. it has to have these like weights and biases that somewhere will be updated to change their state. And as I said, sometimes it needs to be distributed. So some of these things happen on one device, other things happen on the other device. Okay, that's the mental model for TensorFlow. So, okay, at its core, it's a data flow graph with state and tensors on the edges. What is not in all of this is anything about gradients, deep learning, updating, right? All of that is on top of the graph system. It's not in the core processing model. So, for example, gradients are calculated in Python, like going over the graph, and they just add nodes to the graph. Okay, so how do we do this graph in programming? Well, in Python, you import TensorFlow, so this creates just one constant node. Now, to execute a graph, you need to create something called a session, and then session run this node. Okay, so far so good. Now, how do we construct graphs? Well, we have these constants, variable, mathematical operations. Then we have these gradient functions that go over a graph and add a graph of gradients. We have optimizers. So how do we write these things? Well, for example, for a variable, we just say, OK, get variable that constructs a node. You can have assign nodes with variables. So you can say variable assign, something like this. We have nodes for random generators. So you can say, please give me a random tensor of this shape, and that's what it gives. And there are operations like add, multiply matrices, and so on. And now Python being Python, it allows you to overload operators. So instead of like writing every time tf add, multiply something by something and then add something, you can just use plus. So now, when you write an expression like this in TensorFlow, the thing I want you to remember is you're not adding anything to anything in this line. Right? The thing you did is you created a node in the default graph of ops that connects these two nodes, and later, when executed, will perform the addition. So this is a point that's confusing to many people later on. The whole Python part of TensorFlow is just creating a graph. It's like writing another programming language in Python. Only when you run it will it actually execute. Right? So this laziness often confuses many people. On the other hand, it helps like compiler builders and hardware builders because they can only work with the graph. So what operations are there? Well, you can do a lot of things to tensors, right? You can concat slice them, you can sort them, you can multiply matrices, you can calculate averages, you have random operations, convolutions, poolings, and you will learn a bunch of them. And then there are these helpers that compute gradients, that updates your trainable variables. So as I already said, if you have a graph like this, there is this Python function called tfgradients that will walk over it and compute another graph that actually computes the derivative of this output with respect to these variables. And this is just by repeated applications of the chain rule, assuming every single operation has a registered gradient, how to compute gradient of that. Is that clear? Okay, so there was like an example. And right, and then there are optimizers that just apply, like multiply the gradients by a learning rate and apply it. And so the optimizer that's I was talking about, which just takes the gradient, applies by a learning rate, and adds that, is called stochastic gradient descent optimizer. It's the simplest one. But as you will see, it's not very stable. So there are variants of it, like Adam is a very popular one, that are more stable and allow to like less tweaking with training. Also, I mean, we will not do much of distributed execution, but it's good to keep it in mind that there is your graph and there is your session, and this graph will get executed on the same machine, but it could live on a different machine, and also parts of the graph could live on different devices or machines. So it's a distributed system. It only starts to be important if you have 8 GPUs, for example, because then you really want to partition this graph to use all of the computing power of these devices. And also, so now we have the graph. How does it execute? Well, you say, I want this output of this graph, and then it calculates which nodes actually need to be executed to get this output. So make no mistake, TensorFlow is not like an eager programming language that will execute everything from end to end. It has the graph, it goes through the graph, calculates which nodes are needed, and then executes them, potentially executing some of them in parallel. Especially when they're on different devices, a lot of that can happen in parallel, meaning you need to be really careful about state updates if they're of any complexity. If you just want to, because this graph has states, it has variables. So some of these operations might update this variable, and the order of these updates will be undefined if you don't specify it. Luckily, in machine learning, since gradients are additive, it usually doesn't matter in which order these updates happen, but it's something to remember. Also, you have the option, like if you want to substitute a part of your TensorFlow graph with something else, you can always, in the session run command, say feed. I want to change this tensor to some concrete value. And then when it's calculating what it needs to execute, it will not execute the parts that are there, that are not needed. So it's a lazy, like halfway lazy execution system of ops. That's the core TensorFlow model. And now, what you don't want to do is to write matmal, like keep track of every single variable on your own, because it's just not very efficient to keep in your code track of every single trainable variable. There will be maybe 100 of them. You just want something to create it for you and keep track of where it is and update it and just see the results. So for that, we write layers. And layers are like operations. So they create small subgraphs which might contain variables. And so this is like one example of how you would write a layer in TensorFlow. You might add a scope to make sure that like the variable for this layer will not be the same as the variable for another layer. Get a variable and then call an op like matmal or gather or convolution. And like larger models are just built from these layer functions. And often they are parameterized. So when we say a model, it's a singular word, right? You imagine like it's one thing. But usually there are a lot of parameters to tweak. So usually it's actually a class of functions tweaked by like kernel heights, widths, sizes of this or that. And all of these tweaks are, by convention, stored in an object called hparams, which are the hyperparameters of the model. And in some tools, you can then later specify just ranges of these, and it will try to find the best to make your model work best. So these are called hyperparameter tuners. So this is how actual models look, right? They're kind of like these. They're small in code, but they're very parameterized, and they use these layers with a lot of parameters. And then when you train the model, if it takes a few days, you want to save it, which we call checkpointing, every so often. And maybe you want to monitor it. You want to see how the training loss is going down, how it's evaluating, all of these things. So there are tools for doing that. And so there is an estimator API and the TensorBoard. But I think we'll get more to that in the practical setting. So we had this example. Apply a function, like a dense layer, calculate the loss. So how does it actually look in TensorFlow? Well, it looks something like this. You have your input tensor x. The multiply by a matrix and add a bias is called TF layers dense in TensorFlow. So what this function does is it will create the W and B, which will be, you give it a name, so they will be named like H1 kernel and H1 bias, these variables, if you later just wanted to see them or whatever. You need to tell what size this W will have. Like one size is clear from the X, but the other is variable, so you tell it the size. And then it does this. Oh, and if you want the F, you can tell activation equals relu, or activation equals sigmoid, or any function. And then, well, another layer. So if it's an output, it must go to the number of classes that will actually have an output. And then for the loss, we will almost always use something called sparse softmax cross entropy, which maybe I'll get to later. So this is how it looks in equation. This is how it looks in TensorFlow. It's reasonably similar, but keep in mind that this function actually creates nodes in the graph for the variables and for the operations that multiply and add. And then it's waiting for you to call the graph to actually execute these operations. And then something else needs to create the operations for gradients and execute the gradient update. Okay, so what's missing here is where do you get the X? And where do you get the Y, the labels to train? Right? So this is your model. Your model was written in 3 lines, done. We win, but we need to train it on some data. And often actually getting the data and pre-processing it is more work in programming than writing the model. So, well, people used to, well, it's data pre-processing, it's out of our hands. So TensorFlow doesn't do anything for you in that matter. But it's necessary for deep learning. So we created this thing called Tensor-to-Tensor, which is a library. It's a library of models and data sets, but I think we'll focus on the data sets part. So mostly it's bindings for a lot of known data sets in the community. And by bindings, I mean it has a function that says get data. It knows where on the internet this data is located. It downloads it and pre-processes it in the standard way, whatever standard means. Sometimes there are 3 different standard ways. And then it makes it available to you as a queue of tensors. And then it has a bunch of predefined models that people found to work well on these data sets. So now with Tensor-to-Tensor, we can say X and Y is get the MNIST. MNIST is a data set of digits. And you can say get this data set, call this model, and let's train it and see if it recognizes images better. Okay, so I think that was as much as I wanted to tell you about the basics, and now I wanted to go to the code and actually talk a little bit about that. But before it, any questions? Everything is clear. Okay, so let's see how clear it will be when we actually. Okay, so if you had your own copy, then here you can connect to a runtime. So this is Python code, right? But we want to execute it. And this website allows you to connect to a machine in the cloud to execute this code. But if you just click connect, it will connect to a machine with the CPU. While what we really want, what I really want is to find the mouse, but what you want is to connect to a machine with the GPU. Which should be probably here under runtime. Choose runtime type. Oh, I already chose GPU, but you should check if.
Do we have to use Python 2?
This code is exactly the same, so we can use. We can actually go to Python 3. Okay. And then connect. And then that should be it. And then we'll need TensorFlow, tensor, and that. So we need to pip install them. So this is a way that works for like a lecture, but these machines, they disappear after an hour or two. So if you want to train something for a really long time, you need to get to your own computer, either server or get the credits from Błażej and Henrik, and then you'll be able to train in a more serious way. I think I'll leave it for the exercise, which will come soon, to check if actually changing it to TensorFlow GPU works faster. Okay, so this was just a bunch of imports and setting paths, so we can start things. So this is the first. Sorry. This is the first thing that does something. So as I told you, tensor to tensor is this library that has data sets in it. So it has a registry of data sets by name, and one of them is image MNIST, which is this hello world data set.
Is it okay if it's over 100%?
Over 100%?
Yeah.
Whereas
It gets up to 180%, which is a lot of percent.
where is a percent?
Over there, above, at the top of the.
Oh,
It's not even ordered.
yeah, okay.
Even better.
Even better. Yeah, that's just downloading, right? It's just some counters for downloads, which probably misestimated the file size. It's more important what it says here. There should be 60,000 training examples and 10,000 dev examples. That's the statistics of the real MNIST, and it should say that it shuffled them. Yet, did you get there? So first, how do we? So this MNIST is images of digits from 0 to 9 with a label. So how do we get to the tensors, right? We want these tensors like this, batch height with channels. So first we need to get to these images in the height width, just a single image. Height width, and MNIST has just black and white, so it just has one channel. So the way you do it is you say problem.dataset, and then as you saw, it generated like 60,000 training and 10,000 testing examples. So you set the mode. There is a mode train and mode eval that you set. And so this thing is a queue of tensors. This thing is just one set of tensors, targets and labels, because you make an iterator over the queue and then get one, right? And then inputs is the image and targets is the label. And PLT is matplotlib, which can show you the image, right? So let's run it. And this is the image that will be our input, and this is its label, right? And if we rerun it, then we get some other image, right? The training set just iterates through it. So that allows us to verify that we actually have our data in the right order, okay? So now these things are just height, width, and there's just one channel. But we want them in batches, right? That's how machine learning works. You don't update gradients for every example. You take like 100 of them and update gradients for it. So we'll have some batch size. And then these queues of tensors have a bunch of methods. So one is repeat. And repeat means the queue will not end after the final. Like it has 60,000 examples, but maybe you want to train for longer. So repeat it will just restart from the start. And batch says, get me tensors that are that large in the first dimension. So it's all already done towards this convention of batch height width channels.
What is the reasonable size?
For batch size, like 100 is reasonable.
How long does it take to compute 100?
So this is just grouping them. It's just input. It will take the images, group them, right? And then, so you'll see in a moment, right? How long it takes to compute depends on how large the model is. So now, as we said in this problem classes, they come in dictionaries of tensors. And for MNIST, the dictionary has inputs and targets, and inputs is the image and targets is the label. While for other problems, they're sometimes called differently. Like for a question answering problem, there might be like question, context, and answer. So this is specific to the data set, but for many data sets, it's actually inputs and targets. And now, so we take this x and y, as we wrote on the slides, right? X is the image, y is the target. And so I want to make a fully connected network. We'll get into convolutions in a moment. So I'll reshape the x to be something that's just batch size by 28 by 28. 28 is the width and height of these MNIST images. Right? So it's as if I took the image and wrote the RGB values all in one vector of 786 values, right? And then for the labels, they come with one channel dimension, which we don't want. So squeeze is a function that if a dimension is 1, meaning it doesn't really matter, just removes the dimension from the tensor. So that's just preparation for the data. And then this is the model from the slide, right? We have TF layers dense. So we take this x vector from input, multiply it by a 768 by 128 matrix. And as activation, we will have TFNN ReLU, which is exactly max 0x. And we'll give it a name, the hidden thing. Then we will have another hidden layer that will go just into 10 classes because there are 10 digits, 0 to 9. And we'll have another activation. And then we'll have loss, sparse softmax cross entropy with logits. And that's it, but we also want to know how well we are performing in terms of accuracy. So loss is like this log probabilities, hard to interpret. If I have a batch of 100 things, I would like to know how many of them have I actually done correctly? How many times have I predicted the digits in the right way? So the accuracy, so TF equal is a function that checks whether one thing is equal to the other. Our output is a probability distribution over 10 classes, right? It says, I think it's 20% at 2 and 60% at 3. So the actual output, oh, thank you. The actual output, the class number is the argmax of the O on the last dimension. Is that clear? So our output tensor O has shape batch size by 10. Because for every element in the batch, we had this layer that goes into 10 classes, which gets normalized into probabilities of every class. Now, argmax gives the integer, that's the argument with maximal value. So this will give us which digit this output actually have. And we want to check in how many times is it equal to the actual output, to the y. So that's the accuracy. Now all of these operations, both loss and accuracy, they are per element of a batch. So these are still vectors that have a batch, that are batch shaped. So now we take the mean, TF reduced mean, just takes a mean over all dimensions of a tensor. And okay, so we have our loss, and now we need to do these things behind the back, right? We need to calculate the gradient of this loss function with respect to all the trainable parameters which were constructed in these layers, and have the operation that will update them by the derivative of the current loss. And this is all done in this one line. So Adam optimizer is, there are many optimizers. Adam is an optimizer that adjusts the gradients. We will talk about optimizers in a moment, but it could be a SGD optimizer, which would just apply the pure learning rate. And this operation says, yeah, it should take this loss, compute the gradient, and subtract the gradient multiplied by a default learning rate of this optimizer later. Okay, and so that's the model. And not much happens here, because now we're up to train it, right? And in the training loop, as it is in TensorFlow, we need to first run the initializer of the variables. So all these layers, like TF layers dense, they have this set of trainable variables, which are at start random. And at start, they are random uniform, but divided by their size. So the default initializer in TensorFlow is an initializer that tries to make variables that have that would have variance 1 when multiplied by a random vector. Whatever. We don't need to get, it doesn't really matter all that much how you initialize them. You could take a random uniform initializer, or a random normal initializer would also work. And so this line initializes all these trainable variables. And this one, it runs the train operation and will also give us the loss and accuracy, the means, as numbers. And once every 100 steps, we'll just print it out. So as you see, yeah, it's not that slow. And it starts with like 9% accuracy, which is kind of in line with 1 of 10 totally random. And then, yeah, like already at step 100, it has 75% accuracy. And then it goes up, and it's like, well, it gets to about 90 after a very short time. Okay, so it's a reasonable model to recognize digits. This is the accuracy on a training set, right? So what we would normally want to do, because in a training set, well, maybe it has just memorized the examples in training. We really care about accuracy on a separate set where it runs it on the evaluation set. So this is what's done in the code below. So we also want to like reset. If we build the same model again, you remember these operations, they just add things to the default TensorFlow graph. So we might want to reset the graph in the session at some point. Otherwise, we'd be like adding and adding them. Like the new model would live on the side of the previous model and collide with variables. So this is like everything from scratch in one cell. How to get data, how to run a model, and now I added a scope because in the evaluation mode, we will have, well, in this case, the model for training and evaluation is the same. But in many cases, you add extra noise during training, which you don't do during evaluation. So it's actually a different model, but you want to use the same variables in this model. So that's what this reuse argument allows you to do. And other than that, it's the same. And then we have train and loss accuracy, which is the run on training data, and then evaluation accuracy, which is on the evaluation data. So this is the same thing we did before, just grouped together, so you can easily access it later. And this is the training again. So now we can see train loss and accuracy and eval loss and accuracy. And yeah. But in this case, it's a very small model, so it doesn't even, like, they're kind of the same for now. In bigger models, you would see that the train accuracy can be 100% and the eval accuracy will start going down. And that's what you call overfitting, because the model is better on the training data. So I think now you know how to make your own model to recognize digits. So I think it's a time to take some time on your own and do some exercises. So was everything I said clear? Are there questions?
There is some comment about epochs or something.
So an epoch is when you've gone through the whole data set once. That's what people call an epoch. So if we have a batch size of 100, then, and there are 60,000 images, then in 600 steps, we will make one pass through the whole training data. That's called an epoch. And so if we train for 1,200 steps, we actually do 2 passes over the training data. That's why 2 epochs. So an epoch in machine learning is usually referred to as passing through the whole training data once.
So this is a good idea to pass several times.
It's a good idea to train as long as your performance on the evaluation set improves. Which is, sometimes you can pass 100 times through your data set. Some data sets are so large that you never pass even once through them. And actually you might start overfitting even before that. Because maybe your evaluation set comes from a different source. So it's really very problem dependent how long to train. But the usual way is you train until your performance on the evaluation set drops, or until you run out of time, which is actually usually in the models I train at work, you can always train them for longer. You could train them for a year, and they would keep improving. It's just, you don't have that much time, so you set a limit and stop training. Yes?
So there's 2 questions. One is about the idea of the TensorFlow. So the TensorFlow use something like a static graph, and your competitor use something like a dynamic graph. So can you compare these 2 approaches, and to which one is better, maybe from your perspective or from a general perspective? What are the advantages of one versus another? And the second one, for that simple model, I would go for the Keras, because in Keras, to create similar models, you just need like a 5 lines of code. And here you need to care about all of this initializing and all of this stuff. So,
I think you need exactly the same number of lines. I mean, Keras is a different way of writing layers. Instead of tf.layers, you write tf.keras.layers. And they start capitalized. I mean, there is a default initializer here and there, except maybe you have at the end a class where you can call .train. But I would really like to, there are, of course, tools that allow you, so you don't have to write the training loop, they will train for you. But for the purpose of this talk, I think it's good to have the training loop clear. But other than that, I don't think it can get much shorter. I mean, it was like 5 lines. So yeah, on Keras, I think Keras is a very nice way of writing things. TF layers is actually calling Keras. So TF layers dense actually calls TF Keras, calls the same function that TF Keras dense calls. So it's the same code, just in a different. And it will actually become TF Keras in TensorFlow 2. So it will all become the same. On the dynamic graph side, I mean, yeah, so it would be more natural to just write it like the MATLAB style, right? You have the tensor, you multiply it by a matrix every time you have it in your hand. The reason you need a graph is when you want to compile things. Like if you want to take this model, this model, we ran 1,000 steps, it took 20 seconds or whatever. Real world models, it takes a month to train them. So it's a very well invested effort to compile this and make it as fast as possible and add as much static analysis and hardware optimizations and whatever to make it run. So there is this trade-off, right, between writing just in the pure style execute versus the style where you build like a programming thing, but then it can be optimized. And I mean, the hope is that these two styles will also come together at some point, but this is much harder because if you have something that's pre-compiled like this, then of course you have a graph, and changing things in it might become harder. Like maybe you need to rebuild the whole graph. On the other hand, if it's just dynamic, it's hard to compile it, right? So I think both of these approaches are widely recognized. And so like, I guess you mean Torch is renowned for dynamic, but there is now a Torch static package that tries to compile it into a static graph. And it's the same with TensorFlow. There is now TensorFlow Eager, which works in the dynamic mode, which just executes things. So it's like actually both packages have both modes. It's just TensorFlow started with the static one, Torch started with the dynamic one. Google now builds hardware. That's why it started with the static one, because the hardware guys want to, have a graph that they will target. So it's kind of like where people started. The hope is that one day you'll just be able to program dynamically and have a compiler that makes the graph. But it's harder than it sounds. So in some cases, you lose performance with the dynamic part. But in some cases, debugging the static graphs is very painful. Both statements are true, but the best of both worlds, it's not easy to get.
Can you tell us what kinds of graph compilations do you currently do in TensorFlow? Like, can you equal
Yes, there is a fair bit of them. So there's like the standard things like constant folding. If you have two constants and you're adding them, they will be added statically. There are layout optimizations. So for example, as I said, the layout that we usually write for is like batch height with channels. But for example, convolutions on NVIDIA GPUs, they're executed faster in hardware if it's batch channels height width on a different layout of tensors. But then the fully connected layers, they require the channels to be back there. So the optimizer will try to like modify your layout and then keep it, like if there is a row of 4 convolutions, it will keep the layout that's optimized for the GPU and then put it back later. So layout optimization, constant folding.
Layer merging.
Yes. So if you have like a dense layer and then a ReLU, the naive way of implementing it would just make a copy in memory of the tensor. So it would store the activations before, the activations after, and the activations after the max. But maybe you don't need to store one of these things in memory. So you can save memory by merging these into like a single kernel on a GPU. Yeah, I think there is a number of optimizations that I don't even remember anymore. Somewhere when you do session run, you can pass a config argument, which is like a configurator of all these optimizers. And yeah, I don't want to go much into detail. It's something under constant work where people are adding things. Yes?
So there's this function called setScene. And I know that on CPU it works. Like you can train and get exactly the same results, but I have a problem on GPU. I also saw an issue with TensorFlow. Can you shed any more light?
Well, so the layers that we saw, right? They create variables, and they have random initializers, because they will just get a bunch of random numbers and try to initialize things by them. Random initializers have seeds. So there is the TensorFlow setSeed thing, which sets the random thing. And it's supposed to, like when you set one random thing, it's supposed to be deterministic afterwards. But it's not always on GPU because of many reasons. Part of them that on GPU things execute concurrently and sometimes without control of what's happening first and next. And yeah, I mean, I think people are trying to work with NVIDIA to make sure it's actually deterministic. Yes, so it's an open bug, certainly known, but yes. Yeah, it's an interaction between many parts that needs to happen to make sure your computation is really the same. In theory, it's like almost laughable to think that you cannot reproduce results on the same computer, but yeah. Practice, it's harder than it looks like.
And on TPUs, is it reproducible?
Yes. Well, with the recent version of TensorFlow, assuming the TPU doesn't fail, you know. But yeah, but I mean, no, but the principle is it should be, and then people are working to make it so. But I think, yes, I think on TPU it is.
Are there any chances to see TensorFlow C++ built using CMake build system? As of the moment, it uses Buzzer. Buzzer may be nice when I want to start a fresh project, but when I want to integrate TensorFlow into existing project, then change of the build system is out of question.
I think it had a CMake build system for Windows. I don't know what's the status of it, but there certainly was one at one point. I don't remember these details. But yeah, I mean, like just ask, you know, there are all the issues, and just search and ask. Okay, so I think we should get to like our exercises a little bit. Yes.
There will be a break now for 15 minutes.
Yes.
Okay, so that's good.
Perfect. So it's even better. I will just introduce the exercises. So you saw the Colab. I hope you all made copies. So we trained an MNIST model. It's not a very good model. So what I want you to start to understand is, how does the optimizer affect it? How how does the hidden size, the 128 as hidden size of the layer affect it? Like the random thing, if you run it 3 times the same thing, will the results be the same or will they differ by a lot? There is a random initialization happening. What if you change the problem from MNIST to CIFAR, which is like colored images with 10 classes? It's much harder. Would this model still work? What if you change dense layer to convolutionals? And then we can go into more complicated models. But yeah, I mean, in general, what we want to do is to play with these things. And during the break, you can start thinking what's most exciting for you in person to play with, because then maybe we can split like into groups. So not everybody does all of it, but like some group plays with layer sizes and some group plays with, optimizers and some group plays with doing CIFAR. So if you have some idea like how you could group or so, then let's see after the break, and then I'll help you. We'll see how good we can get these models.